I believe we can immediately move on to the first presentation in the symposium. Daoxin, will you introduce the first speaker?
Okay. Okay, so let's move forward to the symposium program and welcome Dr. Chongjin Xie from Alibaba to give the first keynote talk. Dr. Xie will talk about optical interconnects for cloud scale computing. Welcome. Please, Dr. Xie, please share your screen and get start your talk, please.
Okay. Try to share screen.
Okay.
Okay. Can you see it?
Yeah, that's
okay. Thank you, Professor Day, for the introduction, and thank you for organizing committee for inviting me. It's really my pleasure to give a talk here. And good morning for people in Europe, and good afternoon for people in China. And my talk is, the title of my talk is the optical interconnects for cloud scale computing. So I just talk about optical interconnects need and requirements from a user's perspective. So this is the agenda of my talk. So first, a brief introduction. Then I will go to talk about cloud computing infrastructure networks. I go to some details on cloud computing optical technologies, both intra-data center technology and inter-data center technology, DCI technology. So we'll present some future challenges, and at the end I will summarize the talk. And so cloud computing has become the foundation of a new digital business world. Whether you realize it or not, so cloud computing has become a part of our daily life. So when we go online, for example, today, and for work, for conferences, you go shopping, and when you use your map for driving, so basically most of these apps and running on clouds. So there's really a infrastructure for today's digital economy. And it's a transforming our society. And due to the cloud computing, due to the computation power and also the storage we have, so today we have a capability to massively collect data. Then we can have the resource to compute it, to process it, and then give the result and to the all kinds of applications. To give one example, I think people also call it smart city and or city brand, and in various names basically use this technology to want to improve the running of a city. I think our past data shows that, for example, the city brand implemented in Hangzhou, and the data shows that it can improve this driving or your commute time in rush hour by 15%, and it can cut about ambulance time in half using this data and this cloud computing technology in city brand. So then question here is that why you want to move to cloud, right? Many enterprises and business already in the past, they have their own data center. Then what's the advantage of moving to clouds? So basically clouds improve your efficiency, and you don't need to manage all this physical world. For example, you don't need to manage your own data center, don't need to manage your servers, your networks. You can just go grow as you grow. So give one example in the past, and Alibaba has many different businesses. For example, the e-commerce, AliExpress, Taobao, and Tmall, and anti-finance, and today, for example, Ding people use it for office, for it's a working place and online working place. So we used to have all these applications and its own dedicated or data center or hardware. But today, all these applications, all these businesses are running on clouds. So on Alibaba, our own clouds. This is basically customers of our own clouds. Also, the Alibaba clouds provide public service for all kind of businesses, all kind of customers. And so today we are the number 3 in the world for cloud computing. We're number 1 in Asia and China in this market. And clouds are growing very fast, and there is high demand for that. And the data, I think that's from public data, and it shows that in 2020, the global cloud computing market is about $274 billion US. And globally, its growth rate about 20%, and until 2028. So if we do a simple calculation, so by 2028, the global cloud computing market will reach $1 trillion US. And if you look at China cloud computing market, it's about less than 10% today in the world market. It's still quite small, but it's a very, very high growth rate. And I think probably in 10 years, will become much bigger, and not just 10%, it probably can reach 20 to 30% because of the population economy, and definitely will have a big market in the future. And if you look at our own cloud business, so this chart shows that, so in 5 years, our cloud revenue grows by 20 times. This is just revenue-wise. If you look at our infrastructure or network or server numbers, and it's much more than 20 times in 5 years. So there's really a really huge growth and big demand for this service. So what cloud is? Cloud basically it's using scaled solution to provide elastic computing service. So it consists of many small units. This small unit is called a server. So each server, the computation power is limited. But if you wanted to have a large computation power, you just add all these servers together. Right? You put many servers, for example, you can put 40 servers in one rack. And if you want more, you can put many racks, and they form a cluster. And one cluster today can go up to about 100,000 servers. So that's one big network. And they can locate it in one data center or just a couple of close located data center. If you wanted more, then you can have many different data centers. So it's basically a very large distributed computation system. So we used to think that's a cloud or data center just use commodity devices or equipment. But if you look at today's cloud computing, really what they need is a very high performance IT technologies. And they are the main force today to drive the development of IT industry. Here I just list a few examples. For example, you look at a data center, and data center, one big problem here is that its power usage is heat dissipation, and that many innovative ideas to how to cool this, how to increase your power utilization efficiency. And they can use immerse cooling, so people put so basically that's the one of technology we are doing. You put everything in liquid, and you put your server in liquid, you put your transceiver in liquid, you put your networking or switches in liquid. So you can choose can achieve very high called PUE, power utilization efficiency. Can be very close to 1. To 1 means that you don't have any power wasted for just heat. And people also experiment using natural air to cool it without using any air conditioning. And for networking wise, it's really very large scale networking. I will show you later. Is bandwidth. It's really huge, and you not just huge bandwidth, but you have to make sure it's sustainable because it goes very fast. For server, because the cloud computing basically what you provide to your customer is computation power. So that's the server. So today, almost all these big companies, they build their own servers because an open market may not find that the servers that can meet their need. They not only design their own servers, modular servers, they also design their own silicon chips. They can customize their own CPU or GPU, and there are various kind of different processing technology. And not just use today in data center or in these clouds, you not just use CPU, and it's GPU, it's TPU, and various different kinds of processors. And all these companies are working on this processor by themselves because there are different requirements for their different businesses. Another thing is that you need to have not just a few data centers in one place. You really need to have global infrastructure because your customers are worldwide. To provide service to serve your customers well, you need to put your data centers or infrastructure close to them so they can have a better user experience. Or in some countries, they require you have put the data or in their own country. So all these companies have the worldwide infrastructure. I give a map of Alibaba's global data centers. So we have about more than 60 availability zones. This is a term used in cloud computing, and that's called availability zone. That means sometimes just one data center, sometimes just a few data centers. They just to form availability zone. And they also have regions. Regions, I will show you later. Regions, basically, we're talking about a metro area. Our 20 plus regions and our infrastructure located in more than 70 countries and 6 continents. The map here just shows the main data centers. In addition to that, also have many CDN sites or many POP sites. So it's smaller than data center, but it's also need all this infrastructure. We include servers and networking for all this, even for small sites. And for all these servers, all these data centers, you need to have a network to connect them so they can work together to provide the computation power you need. So large scale data center is really it's a key. And here I just, if we look at this chart, so this shows all the network used by data center. And if we from the short distance to long distance, at short distance is inside data center, right? Inside data center, you have many servers located together. You need to have intra-data center network to connect them. And then, as I just talked about, they call it AZ availability zone. So sometimes one data center cannot hold so many servers, and probably in one location or one data center needs about 100,000 servers or 200,000 servers, and your single data center may not be suitable for that, then you have put a few data centers together. They just become campus, and the distance-wise, probably 10 kilometers away, and you really need huge bandwidth over there to form a campus DCI network. And then to next level is a metro network that typically you have few data centers in a region, and to provide redundancy, also provide some synchronization services, and you need a metro DCI network, and also you need to have a global, a wide area network, and it's a backbone network, and they are used to connect different regions together. And you also have an edge network. So edge network have a few different functions. One function is that to connect your users direct to your network. The other thing is that is development of edge computing. Now you have more and more computing power at the edge, and your edge network become probably much more significant in the future. If you look at the data center network, that there's a huge bandwidth requirements. Besides that, right, data center network, there's other requirements. One thing is that availability. They should be always available, because it's like it's an infrastructure. You don't want to sometimes you want to have conference and they just lose everything, cannot talk, and you want to make a payment and you cannot pay, right? You want it available all the time. You want to have low latency, and you have low cost and a high capacity. Here I just give some numbers here about the capacity. Give a few examples. For example, if your the total have 5 million servers, and each server has about 100 gig bandwidth, you can do very simple calculation. The ideal network, if we think the bandwidth is free, right? You want to have full bandwidth communication among any servers. So that means you need about 500 petabits per second at any level. But because bandwidth is really very, very expensive, especially when you go to long distance, and people try to just get some over subscription, go to high level or go to long distance, it reduces the bandwidth. You can use a very simple rule, for example, and inside the data center, you need full bandwidth, you need 500 petabits per second bandwidth. Then you go to metro level, you reduce by 10 times. Then metro bandwidth probably 50 petabits per second. You go to backbone, you reduce by another 10 times. So backbone wide about 5 petabits per second. It's still huge, 5 petabits per second. It's not a small number. It's a backbone. And this is for total network. If you have 5 million servers, we can also do a simple calculation. Say you have, in one data center, you have 100,000 servers. How much bandwidth is needed for this data center? So inside, you can do a simple calculation about 10 petabits. So metro, you do 1 petabits. Go to backbone, that's about 100 terabit per second. Go to backbone, this bandwidth. And all these networks are connected by optics. I mean, almost all, even for some data centers, everything out of a server are connected by optics. But for some other data centers, it's a server still connected by couple. You go to first level switch, then go to next level switch, everything is optics. So you need different kind of optics in data center network. If we can divide them by distance. So first is intra data center, distance-wise about less than 2 kilometers. It's short reach optics. Then you go to a metro level, it's about less than 80 kilometers. And in industry, some one uses just 100 kilometers, but definitely it's less than 100 kilometers. And those distances really are set by the latency. And you have certain latency requirements, then you calculate all latencies. They say, oh, I only allocate this much to the transmission. So then from that, you can calculate distances. Next level is the backbone. That's distance-wise, can be thousands of kilometers. And for example, for network in China and the US and Europe, you definitely have a few thousand kilometer backbone network. And for global network, for submarine, its distance it's more than 10,000 kilometers. It's across the Pacific. And you need to have a large scale for cost-wise and reliability-wise and efficiency-wise. And we really need innovative hardware optics. And also we need to have innovative ways to build and operate this network. And for example, and for our network, we see our traffic grew about 100 times, at least in the past, since I joined Alibaba, we grew about 100% every year. But the operation people, you don't see this number grows. It's about almost same number of people. Even you have double your bandwidth, your traffic every year, you still have similar number of people to operate this network. You really need to have need some automation and intelligence to build a network. So next, I'll talk about these optical technologies. So first, let's look at intra-data center technology. And due to physics, it's really optics side. We use distances to categorize different technology. And from shortest distance, it's about called a short range SR, and that's about 100 meters. This is a multimodal fiber technology. So go to next level, we have 500 meter level, and called DR, called data center reach. The next level is 2 kilometer, and that's called far reach. And then the 10 kilometer reach, the 40 kilometer reach. All this called SR, DR, FR, those are terminologies used by IEEE just to describe different reaches. And if you look at this one, that's from 100 meter to 40 meter, this used to be gray optics that we also call client side. It's not a WDM. And then if you go to longer distance for inter-data center, you use colored optics. So basically DWDM technology. And there's metro distance called ZR, that's about 8 kilometer. And if you go to metro on the long haul, it's more than 100 meters, kilometers to a few thousand kilometers. And you see this red one. So basically those are specific technologies developed for data center. And maybe even 10 years ago, you don't see this DR, FR, and ZR. And what you have is that SR, you either use 100 meter or use 10 kilometer. And those DR and FR, those are specific designed for data center applications. Also, this ZR is just a standard just published last year, specifically designed and developed for metro DCI. So this is a typical intra-data center network. And if you look at this one, so all those here are servers. So your network basically is provide communications between all these servers. You have so many different switches, and ideally if you have only one big switch, that's wonderful, right? You one switch connect all these servers. Economically, it's prohibitive. So you use and they come together to build a network. to connect all the servers. And typically, we have few layers. And for example, here we choose 3 layers. Then go to aggregation switch, then go to core switch. And this architecture is it's very typical architecture for hyperscale data centers. It's called scale-out closed architecture. And in one data center, you have a few thousand of switches. And they are very simple switch, you call commodity switch, and they have lots of fiber links. And the distance-wise, they are not long, it's about a few meters to longer distance, 2 kilometers. On average, inside the data center, your link distance is about a few hundred meters. So data center network really evolve very, very fast. And here I just give an example of how Alibaba's intra-data center network evolution is switch speed. So our network lasts about 10 years from 3.x to 4.x to 5.x, and we are deploying 6.x today. And if you look at server speed, involves from 1 gig and our network, our switch speed went from 10 gig to about 400 gig today. And if you look at it, bandwidth call, this is typical parameter to describe network size called bisectional bandwidth. So basically increased by 100,000 times, not 100,000 times, from terabit to petabits. And if you look at the literature, all the other companies will see similar bandwidth increase in the past decade. And for optics, very beginning, maybe to 40 gig optics, and today massively used is still 100 gig and 200 gig and 400 gig today. So inside that is most of these optical transceivers, and their function basically is that just to convert electrical signal to optical signal, then just go to the other switch. Basically, they're just to extend your switch I/O distance and to increase the I/O speed. So when your I/O speed gets higher, you cannot use copper cable to connect it. You have to go to optics. So it's quite simple. EO conversion, OE conversion, then you to equalize. So multimode technology is still widely used today because the main reason is that it's low cost and power consumption. And the multimode is that you use a VCSEL plus multimode fiber. And a VCSEL is because of vertical light emitting, so you can have a wafer scale testing before you dice it. And for multimode fiber, and it coils much larger than a single mode, so it's easy to align the light, easy to couple light. So all these things make this multimode technology low cost and low power consumption. But distance is limited by mode dispersion. So this technology has been predominantly used up to 40 gig. Then started at 100 gig, people started with single mode, but still widely used today for 100 gig is 100 gig SR4. I think it still will be used for 400 gig. At that time, the per lane speed will be about 100 gig per second. So single mode, this started to be widely used in 100 gig time. And there are two technologies. One is that use multiple wavelengths, for example, 100 CWDM4. And 100 CWDM4 it's specifically developed for data center. Used before that, there's only LR4. So your signal goes to, but can go up to 10 kilometers. If your data center average distance is only about a few hundred meters, is 10 kilometers is really overkill. So you have a high cost and high power consumption. Then it started to have MSA to specifically to develop this technology. They did a few things to reduce cost and power. So first, they increased the channel spacing from 5 nanometer to 20 nanometer. So then you can use uncooled lasers, the free-running lasers. So distance, they reduce distance from 10 kilometers to 2 kilometers. And then they use FEC. LOI does not have FEC, but CWDM, they use FEC. Require a BTR rate and increase from 10 to the minus 12 to about 10 to the minus 5. So all these things together, they relax the specs and they relax the temperature range and relax the link length. That together can reduce the cost and power significantly. Then there's another technology called PSM4. So basically, instead of a wavelength, you say, I just use 4 pairs of fiber to transmit 4 channels. And because your distance short and really cost-wise, it's a good solution. And you don't need to have different wavelengths, and you don't have a WDM max and Dmax. And it also relax your laser wavelength requirements. So PSM reduce distance further from 2 kilometers to 500 meters. And you can use single laser to split them. So all these things and make this is a very attractive technology for data center. Here, I just give one example here for 400 gig of transceiver. So DR basically is it's the same as this. You use 4 pairs of fiber, and PSM4 is used by MSA. Then IEEE adopt this technology. They change the name to DR, so data center reach. If you look at 400 gig optical transceiver, so first you have a DSP chip. The input signal can be 80 by 50, 80 lanes, each lane by 50 PAM4, and then you convert them to 4 by 100 gig PAM4 electrical signal, and you go to drivers, then you go to laser. It can be EML or can be silicon photonics. Then you have 4 pairs of fiber, go to this connector, this MPU connector. And receive side also need 4 pairs fiber, and you have 4 PD array, TI array, and go to DSP chip and go to your host side, go to switch. So you need to have 8 fibers to connect these transceivers. So then next we'll talk about DCI technology. So here I mainly focus on metro DCI, because if you look at your a backbone DCI technology, there's no big difference from the transport technology used in telecom networks, but there are some different requirements here and there, but technology-wise, there's no significant difference. So metro DCI here, I show a few topology. And when you look at when people talk about DCI technology, basically mostly it's point-to-point system. But there are different topologies. It really depends on where data centers are. So first is point-to-point. So those are widely used, especially when you have big data centers in some remote area and huge data centers. They're just about 2 or 3. And you need to just use point-to-point link because the bandwidth requirement is huge. And you better just direct connect them. And next one is that you have probably many data centers, and data center size is smaller than the first one. And you need to have you can have a star architecture or topology, then connect all this data together to two regional center. Then you go to backbone. And another one is that it can be mesh. You connect all these data centers with mesh network, and probably can use ROADM there. And this star and mesh topology, especially in some metropolitan area for big cities. For example, in China, in Shanghai, in Beijing, and you cannot have big size data center. You have probably 20, 30 a small size data center over there. I think that's mesh topology, and the star topology is really good technology to connect them. And distance-wise, all these connections between AZ is less than 100 kilometers. If you look at optical transport system, there are two different kinds. First kind is similar, it's conventional way. You from a switch, use the gray optics to go to an optical transport box. Then you go to a line system. And that means you need to have dedicated optical transponders or transponder boxes. Another thing is that you just use colored optics. You can plug WDM transponders direct to switch. And those, ZR technology is specially developed for this. But today, if you look at what we use today, it's mostly still the up one dedicated optical transponders. Maybe in next few years, you will see more and more of this technology with the deployment of 400 ZR. And for DCI, even we saw lots of research activities and direct detection technology, but in reality, the widely used technology is still coherent. Mainly because it's the advantage in sensitivity, it's insensitive to a line system. The thing is that it's programmable, and this become more and more important in today's network. We see that continued improvement for coherent technology and size, power, and cost. The big chassis system. And today you will see lots of these things become just compact box, like pizza box equipment. But they can achieve a similar capacity. And also you will see more and more of this pluggable. And for example, 400 gig ZR, people are developing can go about 100 kilometers, even longer. In the past 10 years, power per bits reduction is about 20 times. 100 gig used to cost about 100 watt. Today, it can only cost. And we also see channel speed. And also things that you see that about every 2 or 3 years, we're one generation. 4 years, then go to 400 gig, about 3 years. And next year, this year, you see the deployment of 800 gig. And 2 years later, you probably see about 1.2 terabits per channel. And you also see this 400 gig ZR are available today. So when we go to this high speed, we will move from this fixed grid to flex grid. And there's some advantages, and also, for example, it can have a high arbitrary bit rates and high spec efficiency, but it's also because of the flex grid WSS, and they can introduce high cost, high insertion loss for your system. Let's look at future challenges. And this chart is quite busy. I mean, people, if not seen this before, it seems very crowded, but the message is very simple. This is switch chip and evolution in the past 10 years. We see that switch chip capacity doubles every 2 years. And we are using 25 to 6 terabits switch chip today. Next year, we'll see about 50 terabits. 2 years later, you will see about 100 terabits switch chip. And you need to have right optics to get this bandwidth out. And if we see optics evolution, we about from 40 gig to about 400 gig today. You see the challenges here. And we used to have about every 4 years, we have one generation optics. But now you see this, when we get this high and high speed, the optic technology become more diverged. You talk with different companies, they require different technologies for today's chip, not like before. Everybody is 100 gig, everybody is 40 gig. Today, some people use, some companies 400 gig, some companies 200 gig, or some companies 800 gig. It's make the industry or make this whole system really complicated. But definitely we need about over 1 terabit transceiver in 3.5 to 5 years. How to build this in cost and power efficient ways, it's still unknown, still open question. Another thing is that about 5 capacity, I just showed that the per channel evolution of DCI technology. But if we look at capacity or C-band capacity start to saturate, for commercial system, I think that's capacity may saturate about 40 terabits and already use up about here already. So you see that's really your fiber capacity really hitting the limits. And there's some new development in the industry, I mean business-wide. And then we see that we used to have metro DCI. You see in one place you have few data centers, they're distant about 8 kilometers. And today it's one, because this one data center is not large enough to hold so many servers. You need to have few small data centers to form a super big data center. And that distance is quite short, about 10 kilometers, but bandwidth-wise, they require, it's demands much higher than metro DCI. How to build a technology that's more cost-effective than today's 8 kilometers technology? I think it's still a challenge. Another thing is that the industry moving from center cloud to edge clouds. And we used to, all this DCI technology build big pipes. You have few big pipes, but we're going to have many, many small pipes. And how are we going to do it? Still, I think it's still an open question. Then can silicon photonics solve these challenges? I think silicon photonics have very good opportunities here and a scalable solution, and can achieve smaller footprint, lower power consumption. It's really suitable for scale out. It's compatible with CMOS. And silicon photonics already being widely deployed in DC data center, for intra-data center for 100 gig PSM, 100 gig CWDM4, and 400 gig DR4 are already in deployments in data centers. For intra-data center, 400 gig ZR are available today. It's the coherent transponders. And in the future, I think silicon photonics will have high potential. And for example, for co-packaged optics, for 800 ZR, or different shorter reach coherent. So to summarize, cloud computing requires scalable optical interconnect technologies. Hyperscale cloud infrastructure has brought significant changes to the optical communication industry. And it will continue to shape our industry. There are many, many challenges ahead, and we need innovative solutions to solve these challenges. Silicon photonics has demonstrated its feasibility, and we have greater potential in the future. Thank you.
Thank you, Dr. Xie. So there are several questions. Can you see them? If not, I can repeat it. Yeah, okay, you can see the list in Q&A.
Okay.
There are 5 questions.
Okay, what are the main factors that are causing the decrease of bandwidth in nature and backbone? I think the main question here is the cost. And especially when you sometimes when we talk about it with when people build data centers, especially our colleagues, and I think that's a metro area, I think the bandwidths are too expensive. I think that's also reality. If you look at this cost-wise, from 100 meter to 10 kilometer, cost per bit is more than 10 times. If you go to another, for example, go to 100 meters, 100 kilometers, there's another 10 times in cost difference. You just cannot afford to pay this bandwidth. Otherwise, all your costs probably just go to network. If we can, we can build something that's make 100 kilometer bandwidth cost same as 100 meters, that probably can significantly change the whole architecture of your data center, of the network. Okay, second question is that what kind of network standards used in cloud computing, whether SONiC, OC, or OSI, or TCP? I think it depends really. So today, definitely SONiCs are not in today's data center or cloud computing. Predominantly, this is Ethernet technology. And there are different kinds of, when you go to upper layers, TCP/IP, and second layer, it's predominantly Ethernet. There's some InfiniBand for some storage applications, they need very low latency. And I think more and more things will move to even InfiniBand, move to Ethernet. For optics-wise, you want to directly use just Ethernet over optics. You don't want to have many different containers between the Ethernet and the real optics. And for example, for ZI, that to get rid of many different layers, get lost all this OTU layer, ODU layer, just go directly from Ethernet to the optics. So third one is that with respect to slide number 21, 22, how much use a multi-core? Okay. That's this question is about multi-core EDFA or multi-core. I think that's about multi-core or technology. This is a real good question. If the bandwidth increase or traffic increase continue, and I don't see any reason why it cannot continue. And we need more and more fibers. And definitely we need more and more fiber. These fibers were going to be multi-core fiber, is just a 1.5 cable with multi-fiber. I'm still not clear, but for maturity-wise, if you want to use it today or in the next 5 years, I think definitely you want to use multi-fiber cables instead of multi-core fiber. And that's only things that because they are multi-core EDFAs, multi-core fibers, probably I'm still not mature enough for commercial applications. Our next question is about what's next of 400 gig is 800 gig built. that's a very good question. So what's next after 400 gig? And people are already talking about 800 gig, and probably go to 1.6 terabits. It's as I showed in the slides, it's become very divergent today. And different companies, because of their own legacy system, because of their own network architecture, may choose to use different technology. But I think it's better to define this technology in per lane speed. For example, you can see 25 gig per lane is one generation that's used for today's 100 gig system. 100 gig per lane is next generation that will also be, I think, will last very long. That's used for 400 gig transceivers. Next generation after 400 gig, that's 100 gig per lane, should be 200 gig per lane. So you can use 200 gig per lane to build 800 gig transceiver or build 1.6 terabit transceiver. So today's 800 gig people talking about basically used by still 100 gig per lane technology, use 8 by 100 gig. So it's still same generation technology. Let me take the next one. That's about for DCI. Was the review of IP over DWDM by using 400 ZR or ZR Plus from Ali's perspective? We'll use ZR Plus. The only reason for that is that ZR cannot cover all the distances, all the links in our metro network. Not because of distance, because of fiber quality is not good. The fiber have high loss. You need to have ZR Plus to cover the link. Let me see. About intra-DC, will CDR-based transceiver be adopted? Yes, CDR-based transceivers. Today we're using 200 SR4. It's already in deployment today in our network. Is there any alternate to multi-core fiber in data center DCI application? I think I answered this question before. It's still not mature, still in research phase. Next one is 100 gig ZR1. We don't use that. I think some other companies use that for 100 gig DR1, ER1. The last one is about advantage 50-50 nanometer pluggable transceivers. I think the standard is still for clients still 3010. There are some companies really invest a lot on 50-50, but eventually I think it's not get widely used. So that's the reality. Even 50-50 probably is good technology, but there's the standard still 3010. We need to change the standard to get it widely used. Thank you.
Okay, thank you very much for answering so many questions. Okay, so let's thank Dr. Xie again.